Okay, ladies and gentlemen, let's continue with chapter 4 in the textbook of Cengel and Ghajar. Chapter 4 is on transient heat conduction. There are different parts. The first part is the lump system approach. Very, very simple answer, but very limited because it cannot give us different temperatures inside a body. All the temperatures would be the same, and the important assumption is that the internal resistance is negligible in comparison with the external resistance. About 10 times is the ratio. The second approach that we can follow is to look at long plane walls, long cylinders and spheres, and the result of that is that the heat transfer can be in one direction only, not in two directions, and that is why everything should be so long. The result of that was a set of equations which ends up in a Fourier series that we need to solve. And if tau is larger than 0.2, then the error would be less than 2% if we only use n equal 1 as a solution. Okay? Then the third part of the work was we've looked at semi-infinite solids. Semi-infinite solid is a big body, and the temperature doesn't change inside it. It's a very important assumption. And then, very close to the surface, we can see how the temperatures change as a function of time. The last part of the work is now paragraph 4.4, where we look at transient heat conduction in multidimensional bodies. So, from one-dimensional heat transfer, we are now going to move over and make provision or develop the tools so that we can also solve problems where there are two-dimensional and three-dimensional heat transfer. And it is not a part of work on its own. The previous work is used as building blocks inside this material. So previously, we had the long plane wall, and everything was solved as a function of x. Okay? We also had the very long cylinders. Obviously, my sketches are not according to scale. Again, everything was solved as a function of r. The easy one is the sphere, like that. Okay, so this is a long cylinder, and that is the sphere. Okay. Now, the limitation with all of them was that it is one-dimensional heat transfer only. Okay. So, if I can use a different color, if we look at the heat transfer rate, then the heat transfer rate will always be in the x direction, either out of the body or into the body. Okay. Depending on the temperature gradient. But no heat transfer on that surface, and that surface, and that surface, and that surface. Okay. And then the last one that we had was the semi-infinite solid, where we had a big body, and again we've solved everything as a function of x. The semi-infinite solid, and we had a plane wall here on which certain boundary conditions were prescribed or known. All right, so what we're going to do now is we are going to make use of this and make use of a very handy tool which is available in mathematics. And again, that's the reason why you've done it, and that is to make use of the principle of superposition. So the principle of superposition makes it possible for us to use all these solutions to now solve the heat transfer through a body like that, which is now not a long body anymore, and with the heat transfer in the x direction, the y direction, and the z direction. Okay, 3 different heat transfer rates. Okay. So not only in one direction anymore, or the same for the cylinder. The cylinder can now be like that, where previously we have only solved the heat transfer rate in one dimension. Now we can also solve it in that direction also. Okay, now the principle of superposition is subject to two very important limitations. Okay. The first one is all surfaces all surfaces exposed should be to the same temperature and the same heat transfer coefficient on the outside. Okay. So if we now look at this body, then it's very, very important that the temperature on that side is T infinite, on that side also, and the heat transfer coefficient's the same. So the principle of superposition does not work if one of these boundary conditions are different. If I would now change this temperature on this side to another temperature, then we cannot make use of the principle of superposition. Okay, now that is the first assumption, and the other one is actually a very easy one, and that is that Egen is equal to 0. So there's no internal heat that gets into the body because of an electrical resistance element, a nuclear reaction, or anything like that. And that was in any case the assumption that was made when those equations were derived for the long plane wall, the long cylinder, and the sphere. Okay. So the result of that is that when we want to generate, let's call it, the solution for this case, then it is the superposition of the long plane wall and the cylinder, but 90 degrees to each other. So I'm going to try to draw it, and because my sketch is not going to be so good, there's a better sketch in the textbook. So it looks like this. This is now our long plane wall. Okay. Take note, that dimension should be very, very long. Okay, like that. And then the solution for the cylinder. Very, very long cylinder, and there's our cylinder. And the result looks like this. Okay, there's our short cylinder between the two bodies. Okay. The most difficult part of the work in this part of the chapter is not the principle. The most important part are detail on the thickness and the radiuses which are involved. Okay. So that 2L in terms of previously the long plane wall, and this would be R0 like that. And now very importantly is, as I've said, that on the outside, on all exposed surfaces, the temperatures and the heat transfer coefficients must be the same. Then the principle of superposition will work. And the result of this would now be that the temperature, which is now a function of R, X, and T, so now it is a two-dimensional heat transfer problem, minus T infinite divided by Ti minus T infinite for now what we call the short cylinder. For the short cylinder, the solution of that is equal to, let me make it this a little bit shorter. That is equal to the solution for the plane wall plane wall multiplied by the solution for the cylinder. Plane wall multiplied by the solution for the cylinder. Or the long cylinder. Right, so the solution for the short cylinder is the solution for the plane wall multiplied by the solution for the long cylinder. Okay. Now take note that in here we have now x. Okay, and again there's x. So the x position is very, very important in this part of the equation. And in this one, it is obviously r. Okay. So inside that body, our coordinate system is really one of the most important things that you really should take note of. Okay. So the coordinate system, where it is, and from where you measure is very, very important. I didn't draw it in here. We're going to look at it just now. So this is just about the principle. Okay. Now in the test and exams, I'm not going to think of bodies that is going to make it very difficult for you to figure out what you must put together to get that body. Okay. Because that has been done for us. So if we look at table 4.5 in your textbook, in table 4.5 you will see 12 different bodies that can be generated by using the principle of superposition. Now, most probably it is too small for you, so let me enlarge it so that you can see some of it. So there are 12 of them. Okay. And this one is the one that we know is just the infinite cylinder. And this one is called the semi-infinite cylinder. So here you can see it is a long cylinder. Okay. If we come back to this one, the long cylinder, which is infinite, but now we are interested in what is happening only very, very close to that part. Okay. So if this is the very, very long cylinder, then we are interested to know what happens with the temperatures close to that end of the cylinder. This is the cylinder of the short cylinder that we've done just now. And then there are different types of bodies. Okay. Plane walls, corners, etc. Okay. So in total there are 12 of them, and they are very, very useful. In literature there are many more. Okay. But we are not going to consider it because we just want to look at the principle. So if we look at this, then it gives us the solution for the short cylinder. It says the temperature distribution inside it is equal to the solution for a cylinder. Okay, take note of the coordinate system multiplied by the non-dimensionalized solution for a plane wall. And very importantly, look where it puts the coordinate system. So if we look at this short cylinder, like that, then X is defined from there, and R is defined in that direction, and it is in the center. Okay. Again, at the top of the table, it says exactly what I've said here is very, very important, and that is that the temperatures around all the surfaces and the heat transfer coefficients should be the same. Okay. We are going to do problems later on where that is not the case, and it's going to be a trap. But it can be solved very easily. Okay, and I'm going to show you later on. So be very, very careful for that, for this. Okay, so How they write it, how they've written it is that the non-dimensionalized temperature, let's call it the short cylinder, which is a function of R, X, and T, is equal to the non-dimensionalized solution for the plane wall multiplied by the non-dimensionalized solution for the long cylinder. So that is the solution. So, ladies and gentlemen, if we now are interested in the temperature exactly in the center, let's call it T0. Okay. If we want to get the temperature at T0, then it's very important that X should be equal to 0 and R should also be equal to 0. So in the plane wall case, we have to go and get the non-dimensionalized temperature where X is 0, and for the long cylinder, it must be where R is equal to 0. You agree? Okay. The next one is, let's suppose we are interested in the temperature at that point there. So the temperature at that point there would be when X is equal to 0 and R is equal to R0. Okay, if that is equal to R0. Okay. And if we are interested in the temperature there, let's call it T, the temperature at T, then it should be, then we need the solution where X is equal to L. Okay. Because that distance is 2L. Okay. Because this is the plane wall. Okay. And it would be when R is equal to 0. You agree? And then, let's suppose we are interested in the temperature there. Let's call it P. So the temperature at P would be when X is equal to L and R is equal to R0. So, it's very easy. Okay. Can be very, very confusing if you start doing problems. So you have to be very, very careful before the time. Draw yourself a few sketches. Define your axis very, very well in terms of X, R, etc. Because with some of the other problems, it is X, Y, and a Z. And with our equations, they were not developed for Y's and Z's. Everything were developed for X's. So you have to be very, very careful when you do your calculations and the values that you're going to use. Right, the example I'm going to do in showing you how to use this is based on the example 4.8 in your textbook. Okay? So it's similar, but it's not the same one. And the example is a short cylinder. Short cylinder, and it's made from brass. I'm going to read it to you just now. And the K value is given as 110 watts per meter Kelvin. Alpha is equal to 33.9 multiplied by 10 to the minus 6 square meters per second. And at 15 minutes, they want to know the following. If the initial temperature is 120 degrees Celsius, okay, 120 degrees Celsius, and on the outside, the ambient temperature is equal to 25, and the heat transfer coefficient is equal to 60 watts per square meter degree Celsius. The cylinder has a diameter of 100 millimeters and a height of 120 millimeters. Okay, so the problem says a short brass cylinder of a diameter 10 centimeters or 100 millimeters and a height of 12 centimeters, 120 millimeters, is initially at a uniform temperature of 120 degrees Celsius. The cylinder is now placed in atmospheric air at 25 degrees Celsius, where the heat transfer takes place by convection with a heat transfer coefficient of 60 watts per square meter degrees Celsius or Kelvin, and calculate the temperature now at different positions. Okay. What's going to be different is my positions are going to be more than in the textbook, and in the textbook they're going to use Heisler charts. So I'm not going to use Heisler charts, I'm going to calculate it theoretically. Okay. So that you've got both options and you can go and try it at home. Okay. Okay, now the positions that we want, the temperatures are the following. Okay, and they are in the center. Okay, as engineers, normally we are interested in the temperature at the center. Okay. We want to know the temperature there at that position there. Small t4 at the top. And then we also want to know the temperature at that position there. Okay. Okay, now look at the coordinate system. The coordinate system looks like this. X in that direction and R in the radial direction. Okay, now while you finish getting all that information, I would just like to clean the board. Okay, so again, it is based on example 4.8 in your textbook, but it is revised quite a lot. Okay, you all with me? Okay. What I want to ask you now is to divide your page in two, the left-hand side and the right-hand side, because I want some of the information to be approximately next to each other so that you can compare it. Okay. And then at the stage, we're going to converge the two columns into one again, and then later on we're going to do it again. Okay. So let's start with, on the left-hand side of your page, with a plain wall. Okay. The plain wall. And on the right-hand side with a long cylinder. Okay, so what we have here is the plain wall, and the sketches are going to be very critical in developing your understanding in terms of what is happening here, and it is going to make things much easier when you have very complicated problems to solve. Okay. So there's the plane wall, and with the plane wall, that was our center, and that was X. Okay. And X could start from anywhere. It didn't matter, because it was an infinitely long plane wall. Okay. And with that, we had 2L, which was this thickness, and 2L in this case is 120 millimeters. So L is 60 millimeters. Okay. And to get the temperature there, it would obviously be where? It would be that temperature there. So we are first going to get the temperature on that line. Okay. Okay, so on that line, the C's indicate the center of the plane wall. All the C's indicates the center of the plane wall. So very, very importantly is we are going to firstly get the solution for x equal to 0. If we want to get to this temperature here. Okay. Right. If we now look at the previous work that we've done, there's a solution for the plane wall. Okay. In table 4.1, Marilise, if you can just zoom on it for us quickly. The plane wall solution, the non-dimensionalized temperature is equal to that long equation, and the roots are equal to that. Again, remember, the roots there, that 5 should be an equal sign. Okay, it's an error in the textbook. Okay, so what we're going to do now is we are going to use that solution. But before we do that, look here at the bottom, it tells us how should we calculate all the different stuff. Okay, so if we look at that, then you will see that the non-dimensionalized time, the Fourier number, there it is equal to alpha t divided by L square. And it comes from the mathematics. It is not the same number that you will derive in the lump system approach. So be careful for that. Huh? Okay, now alpha is 33.9 multiplied by 10 to the minus 6. Okay, t is 15 minutes multiplied by 60, and L we have. Okay, so let's calculate it. It is 33.9 multiplied by 10 to the minus 6. Okay, 15 minutes multiplied by 60 seconds is 900 seconds. So you can put in 900 or 15 multiplied by 60, doesn't matter, divided by 0.06 square, 0.060, 60 millimeters. So the result is that the non-dimensionalized time is equal to 8.48. So immediately we should be very happy because it's larger than 0.2, okay, which is good news for us. Okay. Then, secondly, let's calculate the Biot number. The Biot number is equal to HL divided by K. The Biot number, the transfer coefficient is 60, L is equal to 0.06, and K is 110, and that gives us a Biot number of 0.03273. If we see such a small Biot number, what does it mean? Okay. A small Biot number means the internal conduction resistance is very small. The internal conduction resistance is very, very small in comparison with the resistance on the outside. So it means that all the delta T's inside the body should be close to each other. So it tells us that if we calculate a temperature there and there, then the temperature differences are not going to be large. Okay? It's going to be small. And then many students would use this gap and say, forget about it. I'm not going to go through all this work calculating all this stuff. I'm going to use the lump system approach. And that's going to be my answer in the test or exam. Okay? I'm going to show to you later on why it doesn't work. Okay. Okay, now again, I'm still busy with a plane wall. Okay. And now with a plane wall, if we now look at the equation, Marilise, if you can look at the equation again for us. There is the equation for the plane wall. So what we need to solve is the following. We need to solve the non-dimensionalized temperature for n equal 1 to infinite of A is the constant in front. A is 4 sin lambda m divided by 2 times lambda n. So it's just everything before the E.
Sorry, so you're just writing the wrong side.
Ah, sorry. Okay, thanks. Okay, yeah. Okay, so, yes, we are still busy with going down here on this side of the column. Okay. So the non-dimensionalized temperature is n equal 1 to infinite of a constant, and I'm going to write the constant down just now, e to the minus lambda n square multiplied by tau multiplied by the cos of lambda n multiplied by x divided by L. And where the roots are lambda n multiplied by tan, lambda n is equal to the Biot number, and because tau is larger than 0.2, we only need to use n equal 1. So we do not have to go and solve the problem for n equal 1, 2, 3, etc. Okay, so that's the first thing that we can notice from this equation. The second thing is, let's look at the cos term. Okay. It's the cos of lambda n multiplied by x divided by L, but x is equal to 0. So the cos of 0 is equal to 1. Okay. So that term becomes much easier to calculate. Okay. So now we can say the non-dimensionalized temperature at C in the center, but remember this center is everywhere on that line, okay, is equal to A1 e to the minus lambda 1 square multiplied by tau. Okay, and A1 is equal to 4 times the sin of lambda 1 divided by 2 times lambda 1 plus the sin of 2 times lambda 1. Okay. So that is what we have to solve. And there are various methods that we can use. You can go and do it numerically. Many packages or computer programs that you can do it with, or you can do it with ease. Okay. I've done it with ease. And we are also going to compare my solution to table 4.2. Because in table 4.2, it would also give us the values for lambda 1 and A1 for different values of the Biot number. Okay. If I can make it a little bit larger. Okay, there you go. Plane wall, the cylinder, and the sphere for different Biot numbers, and we do have the Biot number. The Biot number is 0.03. Okay, so it should be between those two values, should be lambda, and between those two values should be A1. Okay, you agree? You happy with that? And you will see A1 must be approximately 1. And lambda must be between 0.19 and 0.14 approximately. Okay, so you can go and get it from the table, or you can go and solve it. I've solved them, and it gives me lambda 1 is equal to 0.1799, and A1 is equal to 1.005. Okay. Now we can solve the non-dimensionalized temperature on the center line, which is equal to the temperature at the center, Tc, minus T infinite divided by the initial temperature minus T infinite is equal to E to the minus lambda 1 square multiplied by tau. Okay. And I'm still busy going on underneath this. Okay. Okay, let me move to that side of the board. Okay. You will have to help me so that I can keep on writing at the right places. Okay. So now that we do have that, we can solve the temperature at sea minus the temperature at the environment is 25. The initial temperature is 120 and T infinite is 25. The temperature on the outside. Okay, and that is equal to e to the minus lambda 1. And lambda 1 I have solved as 0.1799. Okay, multiplied by tau, which is 8.48. And the result of that is that the temperature is equal to 97.21 degrees Celsius. Okay. So that is the absolute value of the temperature. But in the calculations that we're going to use later on, it is easier to use the non-dimensionalized temperature, theta c. Okay. So theta c is just that term. Okay. So theta c is the temperature at sea minus T infinite. Ti minus T infinite is equal to 97.21 minus 25 divided by 120 minus 25, and the non-dimensionalized temperature is equal to 0.76. Okay. Any questions on this part of the problem, the plane wall? That was the left side of the column. Let's go to the right side of the column. Okay. So for the right side of the column, we are now going to look at the cylinder. And the cylinder, the solution was always determined as a function of R. Okay. And what we are interested in now is to get the temperatures on that line. And let's call it S. So everywhere on that line is the temperatures S. So you have to realize that what we're doing now is getting all the temperatures at R equals 0. Right, so we've already calculated tau, we've already calculated the Biot number. So, Marlies, if you can look at this table for us, if you can zoom in on it, with a Biot number of 0.03, there are the values for the cylinder. Okay? Oops. You agree?
Won't your number change when the formula is HR, okay?
Good. Great. That is one of the traps I've pointed out previously for you. That Biot number, remember, has been calculated for the plane wall. So you cannot now use it for the long cylinder. The Biot number, in terms of how you should calculate it, again, if you look at the solution there, for the cylinder, the Biot number must be calculated as the heat transfer coefficient multiplied by the radius divided by K. Okay. I don't know if you can see it there at the bottom. There it is. Okay. So, and that is why I've left some blank spaces on this side so that you can see they are not the same. So the non-dimensionalized time is equal to alpha t divided by R0 squared. So it is not only the Biot number which is not the same, it is the non-dimensionalized time also. Okay. And that is then equal to alpha, which is 33.9 multiplied by 10 to the minus 6, multiplied by the seconds, which is 900 seconds, 15 minutes multiplied by 60, divided by the radius, which is 50 millimeters. Okay. Because that diameter is 100 millimeters. And the result is that the non-dimensionalized time is 12.2, okay, which is different than the non-dimensionalized time for the plane wall. The same with the Biot number. Calculation of the Biot number is equal to h multiplied by r0 divided by k. The transfer coefficient is 60. The radius is 50 millimeters divided by the thermal conductivity is 110, and that gives us a Biot number of 0.02727. What does it mean if the Biot number is small? It means the resistance of conduction on the inside is small in comparison with the outside. So again, we can say the same thing that we've written here is also valid here. The temperature differences are going to be very, very small. Okay. The equations, however, now looks a little bit more complicated. Okay, let's just zoom in there on the equations. Okay. There's the one for the cylinder. Okay. Although it looks complicated, if you keep calm, then they're actually very easy to solve. So it's not so difficult. Okay. So the solution now, remember we are still busy with the long cylinder, is now that the non-dimensionalized time is equal to n equal 1 to infinite. Again, an, which is just everything before the e value in the equation, multiplied by e to the minus lambda n square multiplied by tau. But now multiplied by the Bessel function of the 0th order, and we have to calculate it at the point lambda n multiplied by r divided by r0. Okay. So I'm writing it a little bit different. And where lambda n multiplied by the first Bessel function in lambda n divided by J0 multiplied by lambda n is now equal to the Biot number. So our roots previously was calculated with this equation, it is now calculated with that equation. And again, tau is larger than 0.2, the non-dimensionalized time, it is 12.2. So we can say we only need to use n equals 1. Okay. And let's see how we can make things a little bit more easier. And we can make it more easier by looking also at this term there. Okay. J0 multiplied by lambda n multiplied by r divided by r0 again, r would be equal to, on that line, okay, so r is equal to 0. Okay. So we want to know what is J0 in the point 0. Okay. You can solve it numerically, or you can look at the tables. There it is. Okay. And it is written as eta. Okay. So that thing there is eta. Okay. So J0, where eta is equal to 0, is equal to 1. Okay. So again, you see the very complicated equation becomes a much easier equation. Okay. And the A that needs to be solved looks a little bit more complicated. 2 times divided by lambda 1 multiplied by J1 lambda n divided by lambda n multiplied by J0 square lambda n plus J1 square multiplied by lambda n. Okay. Sorry for the writing. It's in the textbook. Just go and look at the values in the table. It is given there if I've made an error in the writing. Okay. Okay. So we are still busy on the right-hand side with the problem. You can now go and solve A1 and lambda numerically, or you can get it from the tables. Okay, so table 4.2, or numerically, will then give you values of lambda 1, which is equal to 0.2328, and A1, which is equal to 0.007. So, if we compare these lambda and A values with that of the plane wall, these two are close, but those are not. Okay, and they are not the same in principle. Okay. Again, we can now solve the non-dimensionalized temperature, and the non-dimensionalized temperature we want to solve now is at S. And it's not one point only, it is the whole line on the center. Okay? And that is why I put many S's there. It's not only at one point. Okay. So the non-dimensionalized temperature at S is now equal to the temperature at S minus T infinite, the initial temperature minus T infinite, and that is equal to e to the minus lambda 1 square multiplied by tau. The equation looks the same. Okay, so let's continue here. Still with a long cylinder on the right-hand side of your page. And now we can calculate the temperature at the center minus T infinite, which is 25. The initial temperature, 120 minus 25, is e to the minus 0.2328 square multiplied by tau, which is equal to 12.2. And we can go and solve the temperature at S, which is equal to 74.07 degrees Celsius. And we can also solve the non-dimensionalized temperature at S, which is that term there, which is now 74.07 minus 25 divided by 120 minus 25. So it's those values there, and it gives us a non-dimensionalized temperature of 0.5163. Okay, so far very simple. Do you agree? Nothing new in terms of what you've done previously. Okay, sorry, ladies and gentlemen, we will continue with the next lecture. Thanks, Marlies.